Welcome back to Standard Imaging's discussion of metrology and dosimetry topics for the medical physicist. This tutorial is part of a three-part series on the basic principles surrounding measurements with linear accelerators using a variety of detectors such as ion chambers, diodes, and scintillators, along with the associated electrometers. This segment will discuss special considerations when performing measurements in small fields like those used in stereotactic applications. Before we begin, let's review the major conclusions from Part 1 and Part 2 of our mini-series. From our initial discussions, you should be familiar with how ion chambers and electrometers function, as well as the basic principles regarding their use in standard LINAC setups, especially noting the correction factors that are needed for use with typical dosimetry protocols. To begin, I'd like to start with a working definition of what is meant when someone says small field. In general, when we are thinking about what defines a small field, they usually lack charged particle equilibrium, or CPE. The focal spot is often occluded by the collimators, and on the other end of the equation, the detectors used in small fields often have unique characteristics in regards to their response, size, and composition. We will cover each of these general characteristics in detail in the coming slides. First, let's think about some basic physics principles that we all learned regarding charged particle transport through a volume of interest. For charged particle equilibrium to exist, the number and energy of the particles into a volume must be the same as those leaving a volume. And as we all remember, when CPE exists, the absorbed dose in the volume is equivalent to the collision kerma. If we now consider a large or broad photon field, all of the particles entering are compensated by those leaving, and we have a balance between starters, stoppers, and crossers within the volume. However, if we consider the geometry on the right, which is a narrow field, you can see that that balance no longer exists. Another good thing to keep in mind is that the ratio of the dose to collision kerma, which gives us a measure of the degree of equilibrium or transient equilibrium present in a setup. Considering the dose to kerma ratio, if we look at the following graph, it becomes absolutely clear that for a 6 MV photon beam, which is our most commonly used energy, we need at a minimum a beam radius of approximately 15 millimeters to ensure CPE, which, when we also consider the electron range in the lateral direction as illustrated on the right, we must also acknowledge that this lateral range is nearly independent of energy and equal to the penumbra of the field as well. Thus, one could really feel quote-unquote safe with a field radius of 16 to 20 millimeters to ensure CPE with this energy. The next characteristic of small fields to consider is focal spot occlusion. On these images, it is clear that for a broad field, the entire source is seen by the detector, and we have a large uniform area to work with within our field, so our detectors have no problem measuring dose. However, if we decrease the field size as shown here, it becomes apparent that the source is blocked or occluded by the field-defining collimators, making it difficult to not only perform measurements, but to define a field size as well, as there really isn't anywhere within the field that has a uniform dose, at least with respect to traditional active detectors. If we extend that thought further, as the field size decreases, the traditional definition of field size using the full width at half max becomes irrelevant, as the profiles are obscured by the collimators, and the full width at half max actually gets artificially larger for very small field sizes, as you can see by the illustration on the far right. So now that we've talked about the attributes of the radiation fields themselves, which makes them hard to work with as a small field, let us now consider the detectors available to us and the role they play when trying to make measurements in these very small fields. One of the biggest considerations to make is the fact that our detectors have some finite mass and volume to them, and they are likely non-water equivalent or contain some non-water equivalent components. With these factors combined, there is a perturbation factor for any detector placed in a field which can exhibit volume averaging, energy dependence, and other perturbation factors which may or may not be uniform across field size, energies, or modalities. We'll consider each of these major effects individually in the coming slides. If we first consider volume averaging with regards to ion chambers, it is important to note that the field size for which the chamber is being used in must minimize this effect, allowing for the entire active volume of the chamber to be positioned within a uniform portion of the field. An example, looking at this graph on the right from Kawachi and others, they looked at determining the off-axis ratios in a cyberknife system for which the dose plateau region is very limited, and an approximate 1.5% error in readings can exist if a 24 mm length chamber was utilized in a 6 cm field. And further, a 0.5% underestimation in readings is observed when using a chamber with a cavity length of 3 mm in a 2 cm field, according to this study. Next, let's look at the effect of the detector density, since most of us do not have a calorimeter lying around for a direct measurement of the energy deposited, and our dosimeters are made out of something besides water. This graph shows a Monte Carlo study of the influence of the detector composition as a function of field size, and it is clear by first looking at the tan lines in this graph that the traditional detectors, especially the ion chambers, have a substantial effect in small fields less than 2 cm square because of the non-water equivalence of their components. The diamond and diode detectors are better, although there is still up to a 10% effect at very, very small field sizes. So it should be clear now that the term small field is a bit of a loaded question if you ask someone to define it, as there really is no simple definition. However, for the purposes of this talk, and in agreement with the forthcoming AAPM TG155 report, the main characteristics are as follows, in that the field size is not large enough to ensure lateral CPE in the medium of interest for the energy selected. Further, the source is partially shielded by the collimators as viewed from the point of measurement. And finally, the detector disturbs the fluence. Extending on this definition, small fields have a varying spectra depending on the collimation methods, accelerating potential, field size, and depth. Further, the dose profiles exhibit overlapping penumbra when the fields get small, which results in an apparent widening of the field, which we addressed previously. And finally, there is a drop in output from the expected ideal as the field size decreases as well. Although I could spend an entire webinar talking about each of these characteristics at length, if we consider the conglomerate effect of source occlusion on apparent widening of the field, it becomes clear that the dose as calculated by something like a treatment planning system, which is based on an ideal point source, but in reality, looking at the red lines in this graph, our output does not follow that same curve and has an apparent widening with small fields as well. This graph is another example of this same effect, where our dose calculations in small fields do not follow the ideal point source assumption often made in our theoretical systems, as shown by the red font and corresponding curve, as compared to the blue font as determined with the ideal point source. With regards to relative dosimetry measurements, the TG155 report recommends using appropriate dosimeters for small field measurements and makes specific references to diodes and ion chambers, though it does recommend a backup determination of dose with something like film, TLDs, or Monte Carlo simulations. Listed here are the most commonly used dosimeters, such as chambers, diodes, film, and all of which must be carefully aligned with the machine's central axis, and changes to volume effects along with perturbation factors should be considered when taking measurements at a variety of depths with a percent depth dose style measurement, or PDD curve. Considering output factor measurements, it is important to select a detector that is appropriate as to minimize the energy correction, perturbation, and volume effects, or at least have a dosimeter with known effects, which are often based on published peer-reviewed studies on the topic. This generalized equation shows the parameters that go into determining output factors when considering the ratioed measurements from the standard field, the stopping powers, and any perturbation effects. So now that we have talked about the basics, or well, not so basics, of small fields, I'd like to highlight the detectors and instruments available from standard imaging that can provide effective small field solutions. First, I want to show the latest microionization chamber, which has been investigated at the NRC in Canada for many of the reference class criteria described in the update to GG51. Standard Imaging is the only manufacturer to provide fully guarded microionization chambers, which means the chamber settles rapidly, allows for the determination of meaningful corrections, and has minimal polarity and energy dependence. Combining this with what we learned earlier about field size in CPE, the A26 chamber can be used in small fields for reference type measurements. However, I will note that your exact numbers for something like an output factor may differ slightly from various published values due to the numerous sources of uncertainty with small field dosimetry and the non-uniform characteristics of these fields, as we have discussed. Next, I want to talk about a term coined by Standard Imaging to try and reduce the misuse of the phrase minimum field size when it comes to describing ionization chambers. Standard Imaging has recently started using the phrase spot size to describe the effective pixel size of a chamber. This pixel size or spot size is a reference value which demonstrates a reduction in volume averaging effects and eliminates angular dependencies of volume averaging. And note that this chamber spot size is not a direct measurement of the smallest field size for which the chamber can be used in, as that is dependent on your clinical setup. The A26, for reference, has a 4.3 millimeter spot size. Another instrument for interest of small field measurements, and only available from Standard Imaging, is the W1 Scintillator. This scintillator is a 1x3 cylindrical BGO scintillating crystal attached to a fiber optic cable. This instrument is ideal for small field dosimetry as it is water equivalent, has a linear dose response, is dose rate and energy independent, and there is an automatic Cherenkov correction applied to the measurements when the scintillator is used with the Supermax electrometer. To summarize our discussions today, in small fields there is a lack of lateral CPE, and the source is often occluded by the collimators, along with the other characteristics we discussed previously. For making measurements in small fields, the consensus is to ensure that you have chosen a detector that is suitably small and has minimal perturbation effects. Ensure that your instruments are carefully set up and double-checked. Also, ensure that the correction factors for volume averaging and energy dependence have been determined for whatever dosimeter you're working with, if they are applicable. And finally, compare your measured values with published values, although make note of the fact that there are higher uncertainties associated with small field measurements. Thank you for joining us in our discussions of dosimetry topics. Please refer to the links below to access information on small field measurements, as well as the instrumentation available from Standard Imaging.